Good. So we are still in the process of formulating the GLM for fMRI data analysis, and this is the equation that we are interested in. And last time we went up to what I here put as first point, and then we can maybe talk about this a little bit more. So we talked about independent errors, and this is where we will start today. So we discussed something like this, and then today I would like to continue with that and first discuss what this has kind of an effect on the distribution of the data. So that would be the first thing. And look at an example for this. And then we're going to do the intro to mass univariate fMRI GLM. Or GLM fMRI, whatever. And then I guess we can also start with a stimulus onset convolution. So that would be the plan. So at the end of last week, we actually talked about this idea of independent and identically distributed error terms in the GLM that can also be expressed by a multivariate Gaussian over this epsilon vector with an expectation parameter vector of all zeros and what I call spherical covariance matrix. So this sigma square multiplied by the identity matrix, or the identity matrix multiplied by sigma square. And then we had to stop because the time was running out and I had to move on. So other questions about this, because this is quite crucial. So are you clear about what these three symbols there, so this symbol, and this symbol mean? Are you happy with that? And if not, what is the question?
I'm a bit confused about the general concept, but I know their mathematical notations, their meanings, but I don't know why is that crucial.
Well, it's crucial because we're talking. So it's essentially crucial because we formulate the GLM here always in terms of the distribution of an n-dimensional vector. We also have here an epsilon, which is an n-dimensional vector. And the crucial thing is that we talk, when we talk about the GLM, we talk about a multivariate Gaussian. And the important thing is that this multivariate Gaussian that we are considering arises, and we will see that a little bit more, but arises under the addition of an error vector which models independent errors. So the important thing here is that you are familiar with, I guess, errors that are normally distributed but are according to a univariate Gaussian. And now the important thing is that you view the GLM as arising from a multivariate Gaussian. So that's the crucial thing. And the important thing is that this independence of the errors is encoded in this spherical covariance matrix. So this was this little proof that we looked at last time. So if you multiply the probability density functions of these univariate Gaussians, is the same thing as evaluating the multivariate Gaussian for this expectation vector and for this spherical covariance matrix.
So that means that in the multivariate case, it's not that I guess the error vectors are normally distributed, so it's not a scalar error which is normally distributed, but an error vector.
It's an error vector, yeah. Maybe it also helps if we now look at this thing. It's an error vector, and this vector is multivariate normal distributed and has, because it's a multivariate normal entity, it has a covariance matrix parameter, and this covariance parameter is of a specific form, namely of this form. Maybe we do the second point now, which also basically links the multivariate error more closely to the GLM. And then I ask you again whether things are unclear. So the point that I want to make now, and which is also very important for the entire thing, is the following. This way of writing the GLM, and this is how it's always written everywhere, where of course y is an n-dimensional thing, where n is the number of data points, x is the design matrix with n rows and p columns, beta is the effect size or parameter vector with p entries, and epsilon is of course also then, if it's realized, an n-dimensional entity. This thing is equivalent to saying that the data have a probability density that corresponds to a multivariate Gaussian with expectation parameter x beta and spherical covariance matrix. And I think the one way to see that is to actually do it in a case where one can plot this. Of course, this only really works for two-dimensional things. I mean, could also do it for three-dimensional things, but then it gets a little hard to draw. So I will draw it for 2 dimensions, and you just need to, because usually you have more than 2 data points, obviously you need to kind of extend this to n dimensions. Actually, I like it if it's only 2 people who are actually interested. That's much better than having like 10 people, 8 of them who are like anyway. Good. So let's have a look. So now I'm talking about the 2-dimensional case. So essentially 2 data points. So n would be 2. Hence, the data would be a 2-dimensional vector, and the design matrix would be would have 2 rows, and let's say there's just one parameter value, and so there's only one parameter, and beta would then just be a real number, and our identity matrix would be the 2 by 2 matrix, and of course sigma square is a number larger than 0. So this is the scenario we now want to look at. And to make it even more, now let's leave it at that for the moment, and let's first look at the error. So in this scenario, the error is then distributed according to a multivariate Gaussian with an expectation parameter being 2 zeros and a variance parameter, a covariance parameter being this. So just to make this very explicit, O2 is of course 0, 0, and the covariance matrix is sigma square 0, 0, sigma square. And this is just what these symbols mean. And now let's have a look if we draw from that. So let's say we have roughly, and let's say we have call this x1. No, we'll call it epsilon 1. That's better. Epsilon 1, epsilon 2. And the expectation now for these two arrows is obviously at 0, 0. So this would be our O2 here, which is actually 0, 2. Sorry, it just looks like O2. So that's 0, 0. And now imagine we take samples from this 2 or bivariate Gaussian. What do we get? I now take samples. Hello. What happens if I now take a sample?
Two data points somewhere. Two data points somewhere.
Two data points, or how many data points?
At least one here.
Yeah, but we are drawing something two-dimensional here anyway. Because, I mean, the space that we have here, that's obviously R2, right?
Yeah.
So if I now take a sample, I might sample something here. Yeah? So that would be a sample. And then I take another sample here, another sample here. So if I take now more samples, how does the whole cloud of samples then look?
It will look more linear compared to the previous.
Why? What do you mean by linear? And what?
If we can increase the data point, we can find a fit.
No, I'm just taking samples here.
Samples.
So I'm just sampling this. Yeah, what do you mean by spherical?
They should be randomly distributed.
Yeah, and how does it look?
So there's like a unstructured cloud.
Unstructured cloud, and what kind of shape does this unstructured cloud have?
Small, because it's more closely to, there are a lot of points close to the expectation value and some few more far away.
Yeah, and that's definitely the case. And how does it look in terms of its shape? Is it an oval? Is it a sphere or a circle? Is it a square? Is it a triangle?
So,
Yep. And so it will look something like this, because the roughly and more dots than here, because the two-dimensional because you have to think what's the probability density that is associated with it, right? And the probability density that is associated with such a bivariate normal distribution, as you can also see in the mathematical preliminaries, that of course has the highest density around the expectation, and then has less density to things going outside. And the important thing is because of this covariant structure, which has on the off-diagonal elements, this will not be nice, something like this. Oh, very nice. Something like this. Because of the covariance matrix, which has a for which the off-diagonal elements are 0, this is a circle. If it's if you look at covariance matrices that have, or covariance matrix parameters that have positive things on the off-diagonal elements, you get these elliptical or these ellipses, which are then oriented either like a linear correlation, or like a positive correlation, or like a negative correlation. Yeah, but just make sure that you have these pictures in mind, that they are in the mathematical preliminaries on Gaussian distributions. So it's important. So everything in the script is actually important and will feature here. So it's not that the stuff in there is there just for fun. Okay, so this is the error. Yeah, so it's distributed around 0 and there is no correlation. What does it actually mean that there is no correlation? Well, that means that if you sample something large in epsilon 1, so for example this, then it's actually equally probable to sample something large or small in epsilon 2. Yeah? And this is, of course, it's more likely to sample something that is centered around 0, but once you have, this is a little confusing, once you have sampled something on the epsilon line, so for example you sample this, then it's equally probable to sample something positive for epsilon 2 or something negative for epsilon 2. So it doesn't mean that there's no necessity that if you have sampled something positive in epsilon 1, that you also sample something positive in epsilon 2, which would be the case if you had dependencies. For example, in this case, a positive dependency. If you have negative dependency, of course, then it's more likely if you've sampled something positive in epsilon 1 that you get something negative in, or something, negative or small in epsilon 2. So try to clarify that for you, but that's this spherical notion. Now the important thing is that we in the GLM, of course, we have this epsilon, but then we add to it something that is non-random, namely the design matrix times the beta parameter vector. And for our example here, let's assume that our design matrix is let's say 1, 1, and our beta parameter is 2. So if we form the product of the design matrix and the beta parameter, what do we get? Exactly, so we get 2, 2. And now what the GLM equation says is that we add to each epsilon that we sample, we add the product of the design matrix and the beta parameter vector. So essentially this means now that when we sample something here, so let's now put in some numbers. So let's say this is 1, this is 2, and similar here, so this is 1 and 2 is here. If we sample, or we have already sampled, if we have sampled this point here, we now have to add 2, 2. So what happens with this point?
We will get one additional circle.
Yeah, and where is the circle centered?
In the outside, but I don't know the name of it.
So where's the center of the circle? 2, 2 exactly, because you can either now think that you move each sample, like I started to talk about, or that you move the entire density function. So let's say here, so this is what you find in the script under this name of linear transformation theorem for Gaussian distributions. So here from 0, 0 you add 2, 2, so you get there. Yeah, so that's this plus 2, 2, or which is the same as plus x beta. And you do that to all the samples. So essentially you get all the samples relocated. No, I'm not obviously not doing it for the samples 1 to 1, but kind of just pretending that it's the same samples. But you add 2, 2 to all of these samples here, yeah? And so you move all of them up there, and accordingly, you also have the density over the data then being located up here, something like this. Yeah. And now the crucial thing is if you do this, so we expressed this here as a bivariate normal distribution of this form. And any guesses about the form of this bivariate Gaussian? So it's a bivariate Gaussian. What do you reckon about its parameter? So is the expectation parameter 2 zeros, or what's the expectation parameter? Mu, and more specifically in this case then? Yeah. So and mu is x beta, so 2 2, we can also, instead of we can now either put everything. So we could put 2 2. We can also put mu, and we can also put x beta. It's all the same thing in the current example, yeah. And of course, we will be mainly interested in x beta, where you always need to keep in mind that x beta is a vector. And what about the covariance matrix? So if you look, think again that the covariance matrix encodes the shape of the distribution around the expectation parameter. So has this shape changed, or has it not changed? Not changed. So what do I put there? Yeah, and that, what is the same? What is that? In how many dimensions the identity matrix? Yes. So these are all the same like previously. Now the point here is that if we have this scenario where y is given by x beta plus epsilon, and epsilon is distributed according to a multivariate normal. Now we go to the n-dimensional case with spherical covariance matrix. And we add to epsilon this mu vector, so x times beta. Then saying this is the same as saying that y is distributed according to an n-variate normal distribution with expectation parameter x beta and spherical covariance matrix. Yeah, so this is what we've seen for the two-dimensional case, and now we've seen it. Now we basically just said, okay, instead of 2, we take n, so our x is again n times p, our beta is p-dimensional, our y is n-dimensional. And sigma square still remains a scalar value larger than 0. So now what has changed a little bit, or what the important thing is, that we talk about the distribution of the data. Yeah. So before we talked about the distribution of the errors, to which we always add this mean, but this entails that the data, so y, is assumed to be distributed according to a multivariate Gaussian with expectation parameter x beta and spherical covariance matrix. Yeah? And again, this what this refers to in terms of the spherical covariance matrix this refers to independent and identically distributed error terms. Yeah? So the data, this is also something to be clear about. So if we wouldn't have in this case 2 2, but let's say 2 3, then the data would not be identically distributed. No, it would so it would not be identically distributed because the first data point has an expectation parameter of 2 and the second data point has an expectation parameter of 3. Yeah, so what is IID are the errors. The data are usually not IID. I mean, one can, of course, if one takes the same expectation parameters for all data points, then we also get the IID for the data, but that's usually not the case. And we will see, especially when we talk about fMRI, that of course the expectation for each data point is quite different depending on what currently happens in terms of the experiment. So errors are IID, but data are not IID. Nevertheless, the distribution of data and errors has the same covariance matrix, and the error has a 0 as expectation, and the data have this expectation parameter resulting from multiplying design matrix and the beta parameter vector. Yeah. Questions about this, and maybe no questions again with regard to this here. No? Now everything is clear. Also, good. So so from now on you should always kind of have these two ways of looking at the GLM in your mind. This x beta plus epsilon is what you see often in books and in articles and so on. I also refer to it as the structural form. Main reason for that is because structural equation models are called structural equation models because they have this form. But I think it's usually not referred to as the structural form. But anyway, so I call this structural form because you see the structure of the model a little bit more if you want, because you see that there's this random error added to the deterministic prediction, and I call this, I think, mainly the probabilistic model form or probabilistic form. And I actually favor the probabilistic form because that is like a real probabilistic model where you say, I assume my data are distributed according to this, this, and that. And how you arrive at this distribution, that's of course interesting, and one can discuss. So in this case, we arrive at this distribution because we assume that there's a deterministic component given by the design matrix times the beta parameter, and there's a stochastic component given by the errors. You can also basically come up with other reasoning to arrive at a certain probabilistic structure. For example, in the Bayesian scenario, you would have some price over parameters, and then you arrive at a probabilistic model. So there are different reasons. I think the probabilistic way of considering this is a little bit more explicit because you don't. You make explicit that you model the data, so the observations, as a random variable. So this is really clearly to see here because you say the data have a multivariate normal distribution. In this case, you have to think that because this is a random variable, that y is also a random variable, and it's a little bit more implicit. Yeah. So that's basically that. Good.
Can we say deterministic instead of structure as well?
No, I wouldn't call it deterministic. I mean, the deterministic aspect is only this x beta, but the epsilon is of course also a stochastic or random component. So it's the y being equal to x beta plus epsilon. It's not a deterministic model. If we leave out the epsilon, then we have a deterministic model. But with the epsilon, because epsilon is a random variable, it's also a probabilistic model, but it's just written differently. These are just two ways of writing the same model, but the probabilistic form emphasizes a little bit more that the data is normally distributed, whereas the structural form emphasizes more that the error is normally distributed and is not that explicit about the data. Okay. proceed? Well, let's... I think it's good to have a break now, because although we have only done half an hour, but the next section will be quite different. We will look at pictures and so on, and I will explain the basic intuition of the Mars Univariate fMRI data analysis. So let's take a 10 minutes break now, and then after the break go into looking at pictures and discussing the Mars Univariate approach. Yeah?